Imagine a world of convenience. Moving sidewalks, robot butlers, dinner at the push of a button. The end of world hunger and disease. It might sound like a world out of the Jetsons, or some other science fiction show set in the future, but that's how we thought the world would look like with the discovery of nuclear energy. Man learned to harness the power of the sun and saw themselves as gods, and when presented the power to change the world, they chose to burn it down. Nuclear fission was discovered in 1939 by Otto Hahn and Fritz Strassmann. It took only 2 years before humanity was tasked with a choice: nuclear power or nuclear weapons. By 1941, they were entrenched in the First World War, and after seeing the potential of the atom, opted for the latter. Thus, the following year, the Manhattan Project was established, and on July 16th of 1945, they had tested the first atomic bomb. They didn't wait long to test the destructive power of their new weapon on their enemy. August 6, 1945, a mere 21 days after the successful test in the barren New Mexican desert, the US government dropped the first bomb on Hiroshima, Japan. Between 60,000 and 80,000 people were instantly vaporized by the heat from the blast, with an estimated total death toll of 135,000. Never in the entirety of human history have we had the capability to end life on this scale. Robert Oppenheimer said it best when he described the sheer power of the bomb. Now I have become death, and the destroyer of worlds, and destroy worlds it would. But let's back up a bit. What even is nuclear? How can something so small contain the power to level cities, or power subarctic science stations? Well, let's get into it. First, there are two types of nuclear energy: nuclear fission and nuclear fusion. Nuclear fusion is done in the interior of stars. It requires the right elements and massive gravity to force elements to combine into heavier elements. This bonding of elements creates immense amounts of heat and light, hence why stars glow so bright and hot. Fusion, on the other hand, is the breaking up of atoms into smaller elements. This is the science that we use in nuclear reactors. When atoms split, they release energy in the form of heat and radioactive isotopes. The first nuclear weapons were actually fission-based. Here's how nuclear weapons actually work. When a nuclear warhead is activated, a layer of TNT explosives will blast inward, compressing a layer of nuclear material, typically enriched uranium, into a central core. This causes a fission reaction, resulting in massive bursts of energy. After seeing the true destructive power of the nuclear weapon, the US established the Atomic Energy Commission in 1946 and authorized an experimental reactor. It was built in Idaho and completed in 1951. The first commercial reactor to generate power for the public came online in Pennsylvania, and that happened in 1957. Growth continued well into the 60s, but slowed in the 70s and 80s due to concerns over nuclear safety, waste disposal, and environmental impacts. Despite this, nuclear energy production continued to rise in the US, and by 1991, 22% of all power generated in the US was by nuclear energy. Alright, well, let's talk about how a nuclear reactor actually works. First, the goal of any reactor is to generate electricity by heating water to steam and using that steam to turn turbines to generate power. It all starts with the fuel source. Most reactors use enriched uranium. Uranium is actually found in most rocks and in seawater. Most of the uranium produced in the world comes from Kazakhstan, Canada, Australia, Namibia, Nigeria, and Russia. Combined, the 6 countries are responsible for about 85% of the world's uranium. To extract uranium from rocks, we use a process where we crush the rocks and mix them with water to create a slurry. Then the mixture would be treated with sulfuric acid to remove impurities. That was in the past. Today, we use a process called in situ. Water injected with oxygen or an acid are pumped into the ground, which dissolves the uranium, which is then pumped back to the surface. It is refined and dried, creating a substance called yellowcake or uranium oxide. But yellowcake uranium isn't good enough for reactors. It needs to be enriched. Enrichment is a process where the uranium oxide is turned into a gas called uranium hexafluoride. It's then fed into a centrifuge where it's separated into uranium-235 and uranium-238. U-235 is our target element. Since it's lighter, it can be skimmed off the top of the centrifuge and collected. The collected U-235 is respun to remove any trace particles known as tails or inferior quality U-235, also known as depleted uranium. From here, the purified U-235 is shipped to a fuel fabrication plant and converted into uranium dioxide powder, pressed into discs, and heated to harden into fuel pellets. They are then stacked inside thin tubes, known as fuel rods, and inserted into a reactor, anywhere from 90 to over 200, depending on the size of the reactor. Great, so we have the fuel, we have them in rods and in a reactor. Let's talk about how a nuclear reactor actually works. Inside the core, fuel rods are arranged in a configuration where the atoms coming off of the rods knock into other rods, creating a chain reaction. Water constantly surrounds the fuel rods, which absorbs the heat generated by the fission reaction. That water superheats and turns instantly to steam, and is transported by a pipe to a turbine where it generates electricity. The superheated water is then transported to a cooling tank where the heat from the pipe is taken into the cooling water, cooled down, and sent back into the core. The big cooling tanks that we see have zero radioactive water, so the big clouds of steam that we see rising are nothing but clean water vapor. Awesome. Now that we know how nuclear power works, why would we want to use something that has the potential to go so terribly wrong? Well, it's because nuclear power far exceeds what we've been able to produce in the past. For example, one uranium pellet, the size of a gummy bear, can produce the same amount of power as 17,000 cubic feet of natural gas, 120 barrels of oil, and 2,000 pounds of coal. It's also a great space saver, too. A standard 1,000 megawatt nuclear facility takes up approximately 1 square mile, while standard solar photovoltaic plants on average require 75 times more space to produce the same amount of power, and wind farms often require about 350 times more space. The last two are also dependent on the weather. If it's not sunny, your solar panels don't work. If there's no wind, your wind farms don't produce any electricity. But nuclear facilities can run 24 hours a day. Another thing to consider is if you're taking up all this space for solar and for wind, you're also taking away space from people who need housing, from our ability to grow food. Not only are those aspects, but solar and wind farms also have other environmental aspects that nuclear just doesn't. Solar farms actually increase the ambient temperature of the surrounding area by reflecting sun rays, and wind farms are extremely loud. And because these farms tend to be so large, they have to be located outside of urban centers, requiring their workers to commute to these locations, further increasing carbon footprint. Another thing to look at are the carbon emissions. This is the thing that's actually tearing a hole in the ozone layer. In 2024 alone, coal was responsible for 15.45 billion tons of CO2 being pumped into the atmosphere, with oil at 11.91 billion tons and natural gas being at 7.76 billion tons, all while nuclear is carbon neutral. But how do we actually keep people safe when working in a reactor? The barriers in a typical plant are: the fuel is in a form of a solid ceramic pellet, and radioactive fission products remain largely bound inside these pellets as the fuel is burned. The pellets are packed inside sealed zirconium alloy tubes to form fuel rods. These are confined inside a large steel pressure vessel with walls up to 30 centimeters thick. All this is enclosed inside a robust, reinforced concrete containment structure with walls at least 1 meter thick. This amounts to three significant barriers around the fuel, which itself is stable up to high temperatures. These barriers are monitored continually. The fuel cladding is monitored by measuring the amount of radioactivity in the cooling water. The high-pressure cooling system is monitored by the leak rate of water, and the containment structure by periodically measuring the leak rate of air at least 5 times above atmospheric pressure. Looked at functionally, the three basic safety functions in a nuclear reactor are to control reactivity, to cool the fuel, and to contain radioactive substances. I think it's safe to say that nuclear reactors are, well, safe. But what risks do they still have? Well, for starters, the radiation. If multiple safety systems fail, radioactive material can be released in the environment, as we've seen in Chernobyl and at Fukushima Daiichi. And even as bad as they were, they still don't compare to the deaths linked to other forms of fuel production. From 1965 to 2021, for every terawatt hour of electricity generated, which is used by approximately 150,000 people, coal was responsible for 24.6 deaths, oil being responsible for 18.4, and natural gas being responsible for 2.8, while nuclear sits at a whopping 0.03 deaths per terawatt hours. So let that sink in. Over the last 56 years, non-renewables have caused 1,526% more fatalities than nuclear, including the nuclear disasters that we've had over the last 60 years. But like with nuclear, we do find ways to manage risk in all forms of energy production. For instance, in coal production, the largest risks are things like cave-ins, exposure to chemicals, and of course, miner's lung. Workers are routinely drilled with excavation and escape plans in the case of a collapsed tunnel, and are provided respirators and maintain proper ventilation to prevent respiratory issues and exposure to toxic fumes and chemicals. However, accidents do happen. On April 20th, a bubble of methane gas escaped from the well and shot up the drill pipe, causing the Deepwater Horizon oil rig to explode and sink to the bottom of the Gulf of Mexico, releasing an estimated 3.19 million barrels of oil into the ocean. A combination of wind, ocean waves, and oceanic currents caused the oil to spread to an area of about 5,000 square miles, about the size of Connecticut. The problem with oil spills is that they don't all just rise to the surface. Some of the oil mixes with seawater and bacteria and falls to the seafloor. Some of it clumps together and forms a plume of oil under the surface. Think of this as kind of an underwater sea current, but of oil. There were several methods deployed to clean up oil from the sea. Floating booms were set up around the slick to prevent the surface oil from spreading, and skimmers were used to pull the oil from the surface, though only about 2 to 4% of oil was cleaned this way. After as much oil could be skimmed, they added absorbents to absorb and absolve the oil from the water. Things like peat moss, straw, hay, and sawdust all naturally attract oil, making them great for cleaning the surface of water. They also burned oil from the surface, removing about 5 to 6% of oil from the spill. They also deployed dispersants, which are chemicals that cause the oil to break down into smaller particles, enabling bacteria to break down the oil. So we've created these hazardous waste materials. What do we do with them? That's the ethical question. The lifespan of a fuel rod is anywhere from 3 to 7 years, depending on its location inside the reactor. It's considered spent when the fuel rod can no longer sustain a fission reaction. From there, all U.S. nuclear power plants source spent nuclear fuel rods in spent fuel pools. These pools are made of reinforced concrete several feet thick with steel liners. The water is typically about 40 feet deep and serves both to shield the radiation and cool the rods. As the pools near capacity, utilities move some of the older spent fuel into dry cask storage. These casks are stainless steel canisters surrounded by concrete. Fuel is typically cooled for at least 5 years in a pool before transfer to a cask. Currently, there is no long-term storage facility in the United States. Okay, so now that we understand how nuclear reactors work, let's talk about what happens when they don't. What exactly is a nuclear meltdown? On April 26, 1986, the world would learn. At the Chernobyl nuclear power plant in northern Ukraine, which at the time was part of the Soviet Union, an explosion occurred in Reactor 4. The plant used a type of reactor called an RBMK, which had a flawed design. It was powerful and efficient, but it had major safety weaknesses. To make matters worse, the workers were conducting a late-night safety test that they weren't properly prepared for. The test was meant to check how long the turbines would keep spinning and generating electricity if the reactor lost power, but instead of improving safety, several mistakes during the test triggered a runaway reaction. Here's what went wrong. Operators turned off important safety systems and let the reactor run at a dangerously low power level. In that state, the RBMK reactor became unstable. When they tried to raise the power again, it suddenly surged out of control. The operators hit the emergency shutdown button, but due to the design flaw, the shutdown actually caused an even greater spike in reactivity. Within seconds, the reactor core overheated, causing a massive steam explosion. This blew the 1,000-ton lid off the reactor, exposed the core to the air, and started fires on the roof and in the building. Unlike a typical power plant accident, this explosion released huge amounts of radioactive material into the atmosphere: iodine, cesium, strontium, and other dangerous isotopes. These particles were carried by wind across Ukraine, Belarus, Russia, and even parts of Europe. People living nearby were not warned immediately. Many continued normal routines while being exposed to radiation. It wasn't until Swedish scientists detected unusual radiation levels in their own country that the Soviet Union admitted something had happened. But what's the likelihood of something like this actually happening? Let's put it this way. You're statistically more likely to be struck by lightning or win the lottery. The probability of being a fatality in a nuclear disaster is 1 in a billion, while the probability of being struck by lightning is 1 in 1.25 million. Another perspective, that means that in the entire 8 billion people on the planet, only 8 people would be victims of nuclear disasters, whereas 800 people are likely to get struck by lightning. I don't know about you, but I'd rather make money in nuclear than waste my money in lottery tickets. So, in the end, do the benefits of nuclear energy outweigh its inherent risks? Yes. While nuclear does pose a risk, the risk it poses is far less than assumed by the public. Over the last 60 years, nuclear has provided more energy, more safely, than any and all other forms of energy production by comparison. In 1950, there were no nuclear plants and no energy produced in the world, and by 2023, nuclear is beginning to meet the same energy production levels as coal, oil, and natural gas. That's in the last 60 years. In the US, coal is responsible for nearly 11% of energy, while nuclear sits around about 8. And in the next 60 years, it's expected to bypass and outproduce all forms of fossil fuel energy production, and the change can't come soon enough. With greenhouse emissions on the rise, nuclear aims to solve this crisis by offering clean energy without the release of harmful CO2. And even with the disasters we've had, nature and humanity have such a resiliency to bounce back and reclaim areas we thought would be uninhabitable for hundreds of thousands of years. The Chernobyl exclusion zone has become a nature sanctuary for plants and animals in the absence of humans. Mammals have returned to the area in large numbers with minimal effects of radiation, and has become the largest nature reserve in mainland Europe, covering almost 19,000 square miles. Human efforts to contain the radiation also show human resilience. The levels of radiation in and around the plant are drastically reduced by pouring concrete over radioactive material, and the recent completion of the sarcophagus, a massive man-made structure completely sealing the exploded reactor, further reducing concern for radiation in the area. Members of the public are even able to stay overnight in the buildings of Pripyat, the town that housed the workers of the plant. Not only are human efforts at play to minimize environmental exposure, but the actual output of harmful environmental effects of nuclear power are almost zero. The carbon emissions produced by non-renewables exceed that of nuclear 100-fold, meaning it helps solve the climate crisis. Its land footprint is also much smaller, meaning it can be used for greater purposes like housing or growing food. Within the next 60 years, the world is estimated to run out of oil and natural gas, while coal is estimated to run out in the next 100, meaning the world will need to transition to renewable energy, or nuclear and geothermal. As we run out of our primary fuel, it will grow more expensive, and the race for cheaper and more reliable energy production will increase. Nuclear is on the rise. Not only can nuclear and radiation be used in energy production, it's used all over the world in ways you may not even realize. Radiation is being used to fight the hunger crisis in the world by increasing yield and reducing insect susceptibility in food. Radioactive materials are in smoke detectors and watches. It's also used in sterilization for hospitals and long-term food storage. It's used for carbon dating and even desalination of water. Nuclear isn't going anywhere, and with a world dependent on